Okay, so that probably looks a little bit familiar from our interacting objects and motion problems. And so we've been talking about how energy becomes this very powerful way to solve problems more efficiently and more quickly and a little bit more easy. So we are going to look at the same problem we did in kinematics and forces and interacting objects and see if we can approach it from an energy standpoint. Okay, so here we have a block sliding along the top of the table. The coefficient of kinetic friction between that block and the table is 0.15. It's attached to a frictionless pulley, and this block is falling to the ground. So when the system is released, the block 2 is going to fall to the ground while block 1 is going to move along the table. And the question is, how fast is block 2 going right before it hits the floor? And the floor is 1.5 meters below block 2. So how fast is block 2 going right before it hits the floor? Now, you know how to solve this with kinematics, forces, and interacting objects. So how do we approach it with work? We want to keep in mind that block 2 is changing its energy. It's going from not moving to moving. So there's going to be a change in kinetic energy of block 2. We want to remember that the net work acting on block 2 is going to equal the change in kinetic energy of block 2. So we're going to use that idea to examine what happens. Okay, so let's start with block 2. Now, if we want the net work, we want to keep in mind that work done by any one force is equal to the force times the distance, displacement over which that force is happening in the direction of the force. So that cosine of theta gives us that direction of the force, where theta is the angle between the force and the displacement, and this is really the component of the force in line with the displacement. Okay, so let's do a free body diagram of block 2 to examine what those forces are so that we can look at the force on block 2, or the work done by block 2. So block 2, well, we have the force of gravity acting down, which we know is equal to mg, which is equal to the weight, and we have the tension in the string acting up. So those are our two forces acting on the block. Let's look at the work done by each of them independently so that we can look at that network, the sum of the forces, sum of the work, excuse me. So the work done by the tension, well, that's the tension times the distance that the block travels in the same direction that that force is acting. So we end up with T, which we don't know. The distance is 1.5 meters, and the cosine, I'll just put the angle in, is 180 degrees. So the tension is up where the displacement is down. Now, again, it's okay to put the direction of your displacement to help you frame that angle. Tension is opposite the displacement. So we end up with T times 1.5 times -1, or -1.5 T. I don't know T, but we know the work done by that tension is -1.5 T. Okay, what about the work done by the force of gravity on block 2? Well, that's the force of gravity on block 2 times, again, that displacement times the cosine of the angle. So we have the force of gravity, which is mg. When we know all those values, we'll put our numbers in right away. We have the mass of block 2, which is 2, times 9.8, times the cosine. And now the force of gravity is in the same direction as the distance, times 0. Cosine is 0. So 2 times 9.8 is times 1.4. Oh, we forgot D. Oopsie. That doesn't look right. That's mg times 1.5 times the cosine of 0. And we end up with 29.4 joules. So positive, because the force of gravity is acting in the same direction, so it has positive work. So the net work, if we add these two together, the sum of the work is equal to 29.4 minus 1.5t, and that equals our change in kinetic energy of block 2. All right, so let's look at the change in kinetic energy. We have 29.4 minus 1.5t is equal kinetic energy final minus kinetic energy initial. Well, the block starts from rest, so that goes to 0. And we end up with 29.4 minus 1.5t is equal to 1/2 the mass, 2. Well, let's put it in equation form just so you see all of the steps. M, V final squared. 29.4 minus 1.5t is equal to 1/2, 2 times V final squared. We're going to see we don't have V final, so let's just finish this relationship so we can see that we have 2 unknowns. All right, so we're left with this relationship with 2 unknowns. And keeping in mind, we're probably going to need a little bit more board space, maybe not, but I'm going to rewrite this relationship over here just to keep it straight. This is our first equation. And that first equation has 2 unknowns, which means I need another equation with those same 2 unknowns to solve it. And we want to solve for V final, of course. So just like in our past experience, we look for relationships. Is T related to anything else? Is V final related to anything else? Yes, ask yourself those questions. So is T related to anything else? Yeah, T is the same tension for block 1. That is the same rope. It's non-stretching rope. So we have T. That maybe I can look at block 1. What about V final? Well, block 1 and block 2 are moving together. So not only is T on block 1 equal to the tension on block 2 in magnitude, directions are slightly different. So T, oh, not in this case, sorry. T is pointing up, it's positive. T is pointing to the right, it's also positive. But the velocity final of block 1 is going to equal the velocity final of block 2 in magnitude, okay? So that's it. It tells me to look at block 1. So let's use work energy again, and let's look at block 1. So let's draw a free body diagram of block 1. All right, what are the forces acting on block 1? Well, we have the force of gravity on block 1. We know that's m1g, or weight of block 1. We have the tension. Tension is pointing to the right here. Whoops. So there's T on block 1. We have the normal force pointing up. So the block is sitting on a surface. And we're told that there's friction involved in this case. So we do have friction opposing that motion. That's a kinetic friction because the blocks are actually sliding. All right, so same process. The net work is equal to the change in kinetic energy of block 1. So let's look at the work being done by each one of these forces. So the work done by the normal force, well, that would be N times how far it goes. How far does it go? Well, it's moving with block 2. So block 2 travels 1.5 meters. Block 1 travels 1.5 meters. Oops, that's not what I wanted to do. So D of 1 equals D2. So another relationship. So that's 1.5 times the cosine. Well, again, that's the direction of our distance. They're perpendicular, so that is 90 degrees. That goes to 0. All right? A perpendicular force does no work. We already talked about that conceptually. All right, what about the work done by the tension? Well, that's the tension times 1.5 times the cosine of 0. The tension and the distance are in the same direction. So we end up with a positive, does positive work, positive 1.5 T. Perfect. Now we have the work done by the force of gravity, and that's going to equal the force of gravity times 1.5 times the cosine of negative 90, which also equals 0. And if you infer that those equal 0 because they're perpendicular, great. Your conceptual understanding is solid. I like it. All right. The last one is the force that friction is doing. And so we have the frictional force times 1.5 times the cosine of 180. And so our frictional force does work. It's minus 1.5 times the frictional force. Okay, now we want to keep in mind that that frictional force we know is mu times n. Now I'm given mu in the problem, but I don't know n. And so we do need to recognize that forces are also important, and our force analysis could be important. So if we look at our n, it's in the vertical dimension. There's no motion or change in motion in the vertical dimension, so we know that our vertical forces actually sum to 0. They're in equilibrium. And so let's just examine the vertical forces. We have n in the positive direction and the force of gravity in the negative direction, minus mg. And we find that n is equal to mg based on that mini little force analysis, recognizing that force. So we can use that to determine our frictional force, and we get a value of negative 6.615 joules. All right. So we often have to pull from our resources, and there's nothing wrong with that. Okay, so what does this network then equal? Oops, not n, just the sum right there. Okay, so we have 1.5t minus 6.615, and we know that equals our change in kinetic energy. We're on block 1 here. So we have 1.5t minus 6.615 is equal to kinetic energy final, block 1, minus kinetic energy initial of block 1. And we know that block starts from rest, so our initial kinetic energy is 0. And we end up with 1.5t minus 6.615 is equal to 1/2 v final 1 squared. And simplifying that, getting it into its form with all numbers, 1/2 of 3 is 1.5 v final 1 squared. And so now I have my second equation with both t and v final in it. So I have two equations, 1.5t minus 6.612 is equal to, 1.5. 1.5 got me. 1.5 v final 1 squared. This was v final 2. All right, so v final 1 squared. Well, now I can solve those two equations simultaneously, and I am going to run out of room. So I'm going to erase this part of the board, take a screenshot if you want to keep it handy, and let's go through the math of solving these equations simultaneously to solve for v. That's just algebra. We're going to go through it, but I just want to recap our process before I erase our process. So we have our scenario. We recognize that by moving and by these forces being applied to these two blocks, we're getting a change in kinetic energy. So we can analyze the work being done as a process, as a strategy to determine how fast that block is going. Recognizing the forces, and it empowers us to recognize what work is being done. We want to keep in mind that direction component if it's working with the distance versus against that distance. And then realizing that we have relationships that we have to utilize and what those relationships are. So the idea of attacking a problem, recognizing the most efficient way to solve that problem, and then really those relationships is very, very important. We want to always keep in mind the relationships between objects. And that often presents itself when we have multiple unknowns and we can't solve for what we want without knowing something else. Look for the relationships in that something else. Okay, all right, so let's go ahead and erase this. And we will get our finished product. So if we are solving two equations simultaneously, there's of course more than one method to do that. My favorite method is substitution. So I like to solve for one and plug it into the other. So let's solve for t in this equation, because that's what I did in my notes. And my first time you can solve for t in this equation and plug it in. You can solve for v final and plug it in. I choose solving for t because then I eliminate t and I solve for v final, which is what I want to do right away. So we'll start with that. So 29.4 minus 1.5t is equal to v final 2 squared. All right, we're going to solve for t. So we have minus 1.5t is equal to v final. Well, it's now v final. We don't need the 2 anymore because of this relationship. V final squared minus 29.4. And so t is equal to 29.4 minus v final squared all over 1.5. So I divide by a negative 1.5. That reverses that numerator and leaves 1.5 in the bottom. So now that I have t, we're going to take t and we're going to plug it in to this relationship. Oops, I didn't give myself enough room with my arrow. There we go. All right. So 1.5 times the quantity, 29.4 minus v final squared, all over 1.5, minus 6.612 equals 1.5 v final squared. My 1.5 cancels. I end up with 29.4 minus v final squared minus 6.612 equals 1.5 v final squared. When we bring v final over, collapse those two, we end up with 22.785 is equal to, add 1, 2.5 v final squared. And when I solve for v final, I end up with 3.02 meters per second. All right, so recognizing relationships and the power of the work-energy theorem and recognizing that if forces are doing work on an object, they're going to change its kinetic energy and solving problems that way. All right, nice work.